Hello and welcome to this talk in this online conference experiment. First of all, thanks to the organizers for putting it together. It seems to be very well organized. My talk will be based on a joint work with Oleg Budkovsky and Konstantinos Daraiotis. And the topic is approximation of SDs with irregular drift. So the setup looks as follows: that you start with a differential equation with some driving coefficient b, and you add some noise, which in particular allows you to take quite irregular b. So without the noise, this ODE needs basically local Lipschitz b to be evaporated, to have existence and uniqueness of solutions. But when you add noise, you need quite a bit less. And what we are interested in is the approximation properties of these equations. So how can you discretize them, and how well discretizations, and in particular classically well-known discretizations, perform. So what is the difference to the kind of classical setting, which would be SDs with, let's say, a regular B here? So in that case, the solution can be realized as the fixed point of a contraction map, which is based on some nice operations. So you chain together, you put together some nice operations. So you first compose with the coefficients, then you integrate, then you add the noise. And if all of the operations here are nice, then it's not so surprising that if you change one of the operations in the appropriate topology a little bit, then the solution will change a little bit. And in particular, this applies to discrete approximations because, for example, an Euler approximation of this equation is nothing but the solution of this fixed point map. Then this integration operation is replaced by an appropriate Riemann sum. Of course, this approach is bound to fail for these equations because B is not nice. So you have to do something else, and the something else has to really exploit the noise and the regularization effects of it. So when the noise is a standard Brownian motion or some alpha stable wave process, this has been looked at. Here's a list of references which is definitely incomplete, so sorry about that. And also sorry about not giving too much details about this due to time constraints. One comment that I want to make is that actually this work will also have a talk in this session. So if you're interested, you can check that out. And the more mathematical comment is that there is sort of a common theme in all of the existing literature, which is what we refer to as PD method. So this is an approach in the regularization by noise business going back to Zvonkin and Veretennikov, which simply put relies on the fact that you can find a phi such that phi of x solves an SD with a regular drift. Usually you find the phi by solving some PDEs, so this is where the name comes from. But this also kind of shows the limitations of this approach. That first of all, you need the Ito's formula, which is for some different types of noises might not be available or might not be useful. But also there's another kind of more subtle limitation, is that doing this will lead to suboptimal rates. So I will be more concrete about this when I talk about concrete results. So I will mention two results corresponding to these two limitations and how we can overcome them. So the V means this work, where what we do is instead of going to this Zvonkin-Veretennikov approach, we go and try to apply sewing methods in this for this question, which goes back to, well, actually it goes back to Yang integration, but in this context it was developed by Kubinelli, and then a recent very relevant variant is by Coalet. And so we want to kind of implement these ideas in the question of discrete approximations. So I will just mention the basically two main results that we can get with this, and how this overcomes these limitations of the PD approach. So the first is when you look at just additive noise, but fractional noise. Of course, here Ito's formula will not be very useful to remove the irregularity of the drift. So BH is a fractional Brownian motion with first parameter H, and you take a drift which is in C alpha, and it is well known that you need some regularity of B to be well posed, which is of course way beyond way below Lipschitz. In particular, when H is less than 1/2, this gives you a negative lower bound. So in principle, B could be a distribution. But of course, to look at the Euler approximation, which is this one, so where K and T is just the last grid point before time T, when the grid is of a mesh size 1/n. So this is just really just the usual Euler approximation with extended to continuous time. So to make sense of this one, you definitely don't want B to be a distribution, because you don't want to evaluate the distribution at single points. So this leads to a kind of other natural condition, which is that alpha should be non-negative. And I should also mention what do we mean by C alpha, because the Euler spaces usually at integer values are a bit ambiguous how to define them. So the way we understand them is that C0 is just bounded measurable functions, not necessarily continuous. C1 is Lipschitz continuous functions, and so on. So it's not surprising that, given the fact that the literature is based on PDE method, that this is not, there is no results that we could find that deals with any kind of irregular drift in the fractional Brownian case. And what we managed to prove is the following: that if you just assume these kind of minimal assumptions, so for the well-posedness of the first equations and this one for the well-posedness of the second equation, then you have convergence and you have rate of convergence. So let's go through this estimate, what this says. So first of all, it's, we measure the error of the two, the discrete solution and the true solution, in a quite strong topology. So it's in particular much more strong than just taking the supreme norm of the difference. Then in omega, you can take any piece moment, which in particular gives you also convergence and the rate of convergence almost surely. And the rate, well, there's a small loss of epsilon, which can be arbitrarily small, so not so important. You cannot go above rate 1, which is also not so surprising. So really the main content is this 1/2 plus alpha h, which in particular shows you that, well, as long as these conditions are met, no matter how small alpha and how small h is, you really get a positive and not completely rubbish rate. And okay, I don't have time to justify this 1/2 plus alpha h. Why is that natural? So this is left for exercises for the interested viewer. And let me go to the second result, which is concerns a situation which has been looked at with PD methods. So it's standard Brownian noise, but multiplicative. So in this case, of course, the diffusion coefficient is assumed to be non-degenerate and reasonably regular. And here, what has been proved is rate 1/2, and we also know that we cannot expect better than rate of alpha over 2, and we cannot expect better than rate 1/2, right? So this is what. Okay, so what we can do with the Sewing method is to show that this kind of optimal rate is always achieved, no matter how small your alpha is, as long as it's positive. So okay, we have the same story as before, although in this case the topology is slightly worse than Höldermann-Hoof, but still much better than Suplimum, and any piece moment, and so on. So this is what I meant by kind of the suboptimal results from the PD method, which give you, well, for very small rate. These can actually be improved to the optimal rate of convergence with the sewing method. Okay, so I'm already over time, and this is a good time to stop then. And thanks for the attention. Right, thanks.